Hi guys, I'm going to be going through electricity and motors, etc. for Unit 4 physics. Starting with magnets and motors, going through the flux and generators, and ending up with how transformers work, and transmission lines, how they actually work. But first, we'll start with the basic magnet, the simple magnet. Okay, so what a magnet does is that there's a north and a south pole, and it goes from north to south. That's all I want to tell you. And to figure out what its field is at point P, all you need to do is draw the line there. So if it goes from north to south, which means it goes in at south and out at north, at point P, this magnetic field will be going to the right. Finally, to figure out how the interaction of two magnets work together, is that you just need to add them both at point P. So point P, we know this magnet is having an influence of pushing it to the right. Okay, all I did was just draw the line. And then now I have this. So what would happen here? Well, we know that the line goes inwards into south, out of north. So it must be having an effect of going down. So now this magnet's pushing it to the right, this magnet's pulling P down. The net effect of the field is this way, going diagonally down right. So you can imagine doing it like this. So the types of questions they have that you see, just let me find one. Here's one. This is actually the exact same question. Field going to the right, field going down. What's the field at point P? Diagonally down right. So the next part is, now we need to incorporate the Earth's direction of the Earth's magnetic field. So the question asks, what is the direction of the combined magnetic field of the bar magnets and the Earth? So we have 1, 2, 3. Well, we know at point P, it's going that way because of this magnet. This one's just going down. All we're doing is drawing in the lines. So continue. And we also know that Earth is going up. So now we're adding down, plus across, plus up. And these will just cancel, and we end up with across. So that's pretty much all you need to know about magnets. So now the right-hand rule, right-hand grip rule. So I know that you have had a bit of headache with this, but it's not that hard, okay? What it is you have a current, okay? So as soon as you have a current, it tells you, the right-hand grip rule tells you which direction the field will go. You just put your thumb in the direction of the current, and once you get it there, don't ever let go. Keep your thumb there no matter what. And then you just put your fingers around, just like that hand, and you figure out the field must be going that direction. So that's all well and good, but sometimes in a coil it gets more confusing. So what you need to do is just look at one individual section of the coil. Copy the hand there. So here we know the current is going down, so we put our thumb there. Don't let go. And then we just have to put our fingers inside the coil. So our thumb, we could kind of rotate around everywhere, but we know the inside of the coil is inside, deeper in, so we need to put our fingers that way. And therefore our field will be going that direction, and then we can draw the upper lines like that. So the kind of question that we see for this is something like this. This is a coil, so we have a positive direction, so we know the current is going up. So what I do is I look at an individual coil out of this solenoid. And so here I'm going to put my finger going up. And now I want my fingers inside the coil. It's no good if it's outside. If it's inside, it shows me that this is the direction of the field. Fingers are always field. So therefore on the inside it must be going to the right. And if we need to draw 3 magnetic field lines, it's easy. We just draw it like this. Must be going this direction. So you can even test it if you want. On the outside, you put your thumb up. My finger's now on the outside. It should be turning to the right. Sorry, did I say right before? I meant this must be going to the left. Yeah, so that's what you do with the right hand grip rule. Place you use it is when you have current and they want field. Because that's different to the right hand grip rule where they give you current and a field and they want force. I mean, that's different from the right hand slap rule. This is right hand slap rule, this is right hand grip rule. Okay, slapping looks like this. This is how you slap. So, right hand slap rule. If we have a current and a field, so current going this way, field going that way, we slap into the page. It's kind of fun. And that's the direction of the force. And this just tells us F equals NI/LB. This is just how much force happens. So the kind of questions we get from that is something like this situation. So this is the same coil as up here, so I know it's going to the left. It's going to the left. And that's our field. Now they're asking us, what's the force on PQ? What direction is it? Direction of force on PQ. So what we need is, ask for a force, we need to use the right-hand slap rule. We need the current, and we have the field. So the current's going towards us. Just check for yourself. It's going towards us. Field's going that way, so it must be going down, because we slapped down. Force on PQ is going down. Now, what is the how large is it? We have F equals NILB. So N is the number of turns. Where is it? Turns. Current. I is current. L is the length. B is the field. So if they're asking us for how much force, because that's what these formulas are actually for. Pretty much they'll just tell you how much things are. They never tell you directions. Well, you need to find all those individual bits. So N, there are 3 turns of wire. How much current is there? 4 amps. What's the length? PQ, that is 4 centimeters. So that's 4 times 10 to the negative 2. And then times B, the field is 5 times 10 to the negative 2. And I'm going to do that in my head, which I'm not, but that's okay. You guys can solve it yourself. That's how you do things with the right-hand slap rule. So now this is really cool, because now we can make a motor. All we need is some current, some field, and we know things move, because that's what we just shown. We just shown things move by the right-hand slap rule. So how does this motor work? If we put current up in through here, and then we have a field going off to the right, this must go down. Okay, but then there's commutators and slip rings. It gets a bit more complicated, and we're going to go over that right now. So here is my magnetic field. Okay, and this can be our little coil thing. So initially the current's going in, and we can see from our right-hand slap rule that this side is going in, field's going that way, should be going down. So once it gets all the way to the bottom, what happens then? Well, if we look at this, the current's still going in, and then the field's going off to the right. So now it's just going to keep pushing down, but it can't go any further down. So our motor is pretty useless unless we do something about it. Somehow we need to switch the currents, because now if we switch the currents and this is coming out, and then we put our fingers in the direction of the field in north to south, now this bottom part will be going up. So we'll go up to the top, and now what happens? It can't get any further up, so all we do is we switch the current again. So we need to keep switching these to make the motor work. Now there are 2 ways to switch these. One is with a commutator, and that's when we actually physically switch it. See, if we made everything on this side positive and everything on this side negative, like we just connect it here. And these are the split rings, because it's split. That's why it makes a lot of sense. You can see the red is always on the left, but now it swaps, because the red is always on the left. The positive side is always on the left, because the direction of the current will now swap. So that's how a commutator works. And commutators are used for DC, because DC, there's always one positive and one negative. Now the AC one, we don't need a split ring. This is a split ring. This is a commutator. And these 3 words all go together. Now an AC doesn't need anything like that. AC automatically swaps, because AC goes like this. That's AC. So all we need is 2 slip rings. Because once it gets to the bottom, the AC is going to swap. Anyway. So, how do we use this in a question? Because that's what you guys all really care about. It's exam time, I know. Explain the functions, the difference in function between a split ring commutator and a slip ring. So first of all, a split ring looks like this. And what it does is it reverses the current every half turn. So that's split ring, and that's a commutator. I'm just going to circle this so it's faster. Okay, and this describes this issue, and this is used for DC, because in DC, there's always one positive, one negative, and it's not being reversed. The DC isn't going to switch around. The DC is just flat, okay? Whereas the AC can use a slip ring. And the slip ring, all the slip ring does is connects the, what do I call this thing? Connects the internal segment to the battery, to the power source. And a perfect example of a slip ring is this. You see how it just connects it, and it's just going to keep rotating around. It's connected to Q. This is a AC support source. Whereas a split ring would look like this. Yeah, and for AC, that's pretty much it. It just connects it. So for DC, it reverses the current every half turn. That enables torque to be in the same direction. It's used for DC. AC, they just need slip rings, and we just connect that to the power source. And that's pretty much magnets and motors. I hope that helps. I'll be moving on to flux and generators next. Cheers.